All right. Hello, everyone. So this week, what did we do? We talked about Schur's lemmas, and then today I have started with discussing the characters of representations, right? But let's just remember where we were in the previous week. We have said something like that, right? First of all, and there are these two properties in here. So if G is a finite group, every representation is equivalent to a unitary representation. All right? I mean, if the group is a finite group, then whatever the representation is, and in a matrix representation, I can make a symmetric transformation where every representation is a unitary representation. So that's the first statement. And second thing is that if a unitary representation is reducible, let me express it like that, then it is completely reducible. But we have expressed this in terms of the invariant subspaces, actually. So if a unitary representation has an invariant subspace, then the orthogonal complement of that invariant subspace is also invariant. But this essentially means the same thing as this one. So reducible means that A is equivalent to a representation where there are these block diagonal terms in here. There's also some part in here which is also probably non-zero, but this part is zero. So therefore, this is like a block upper diagonal matrix or something like that, right? So that's basically what reducibility means. Completely reducible means that this is in block diagonal form, which means that it's a direct sum of representations, right? Whatever, I mean, so as a result, I mean, if the representation is not unitary and we have an infinite group, this implication is not true. Right? There are examples where we have representations which are reducible, but it's not completely reducible. Okay, but let's just leave them aside. So this basically tells you that, right, if G is a finite group, okay, because of the fact that every representation is equivalent to a unitary representation, so that means that this property, the second property, holds for every representation. So any representation which is reducible is completely reducible. Right? If G is a finite group, then any representation A can be written as a direct sum of irreducible representations. Okay. So for every representation A, therefore, I can do some kind of a similarity transformation and pass to a new representation. Let's just write it down like that, where we have this thing in block diagonal form, so there are some representations in here. So let me call this as B and this as C and I don't know, D and so on, right? Lots of representations in here. And all of these off-diagonal blocks are equal to zero. Right? If it is reducible, then it can be brought into that form. And I can continue this for each diagonal block. So if that block is, for example, is reducible, I can make this as block diagonal in smaller blocks. So I'm going to assume that I have done this all the way through. So as a result, each block that appears in here is irreducible, right? It's not reducible. Okay. So it's basically a decomposition of a representation in terms of irreducible representations. Okay. So from now on, this is a term that we are going to use a lot So I'm going to call them as irrep, as a shortened form, all right? Because writing irreducible representations takes a lot of time. That's the reason why. Second, for each irreducible representation, I'm going to find, I can take similarity transformations and find equivalent representations, but they are really not different actually. So I'm going to get, I'm assuming that I'm just going to select a representation from each irreducible representation. But since the group is finite, I can assume that these are unitary, right? So let U1, U2, and UC be the irreducible representations of, let's say, the complete set of inequivalent irreps of the group. Okay, meaning that they are irreducible. So that's the first thing. I'm finding them. I choose them to be irreducible. Let's say such that each of these U mu is a unitary representation. I'm going to choose them to be unitary. I'm going to call let D mu be the dimension, right? So that means each U mu G is a E mu by E mu matrix, right? Okay. So yeah, whatever. There's this dimension that we are going to use a lot actually. And I'm also assuming that if mu is not equal to mu, so if we have like different representations, then they are not equivalent to each other. So they are not related by a similarity transformation to each other. If they are equivalent, then I don't need to make a list of them. In any case, let's see. All right. So let me just think about it. So in any case, here C is the total number of inequivalent irreps of the group. Okay, sometimes I'm just going to call this as like the total number of representations, irreps, total number of irreps, right? Total number of irreducible representations. But what I mean is that by just a set of inequivalent irreducible representations, right? But there's some arbitrariness in choosing these matrices, right? Because I can make a similarity transformation and still I get a representation which is equivalent to that. So as a result, there's some arbitrariness in here. But once we choose this set of matrices, then that means there's some kind of a, I can basically decompose any given representation as a direct sum of these. Okay? So let's say A is any representation. So that means, there is an invertible matrix S where from A to, let's say, we pass to a new representation, which is given by that similarity transformation. So let's say these are functions of the group element as well, where this A prime is in the block diagonal form, where we have the U1 in here as the first block. So this might be repeated many times, right? So U1 is repeated like that. And then we have, sorry about that, we don't have much space left in here. Okay, so this kind of a notation becomes cumbersome after some point, right? So there's also a number of times that U2 is repeated and so on, right? This can be a very large matrix, but we are going to bring them into the block diagonal form. So I'm going to use M1 to to be the number of times that first irrep appears. M2 is the number of times second irrep appears, and so on. Sorry, what did I do? All right. So M mu is the number of times U mu appears in the decomposition of A. Okay. So in that case, of course, the correct notation, line notation for this is that A is a direct sum of, well, this is equivalent to a direct sum of U1, and so on. This should appear M1 times, and so on. Right? I mean, let me just write this like that. So as a result, we have M1 times U1 appears in here, M2 times U2 appears, etc. There's a very nice shorthand notation that we are going to use. So if it appears like M1 times, I'm going to write this expression as M1 times U1. Okay. By this, I don't actually mean that U1 matrices are multiplied with M1. It's just that the U1 appears in here M1 times, right? So that's a notation that we are going to keep using. Okay. There are a few other questions that might also appear in here. How do I know that there are only a finite number of irreducible representations? This is going to come out later. Perhaps today too, I can talk about this. And how do we find, I mean, which irreducible representation appears how many times? We are also going to produce some kind of a mathematical technique for computing these coefficients, for example, right? Just keep this in mind. Let's just note that in here, M mu is an integer starting from, well, it's a non-negative integer, right? So it can be a positive integer or zero. Zero if that representation doesn't appear. Right? Just keep this in mind. Okay. Do I have to say anything else in here? So the idea in here is this. If I have a certain representation, basically, when we want to solve a problem, like, for example, I would like to compute the energy levels of the methane molecule. Right? Methane is a very nice molecule, right? CH4. It's in the shape of a tetrahedron, actually. So there's a central carbon atom, and then there's a central carbon atom, and then there are like 4 hydrogen atoms in here, arranged at the corners of a tetrahedron. So it has a nice symmetry group, for example. So suppose I would like to solve the energy level problem for this. Sorry about that. Let me close some windows. So I would like to find the energy levels of that. So I need to find, in that case, I need to construct an Hamiltonian. Well, the Hamiltonian is actually kind of known, but this is actually a very large problem with an infinite dimensional space of all possible wave functions. Usually when we are solving this kind of a problem, we just take a set of some molecular orbitals and things like that, and then try to construct the wave functions as a linear combination of them. In any case, with this approximation, we actually get some kind of a Hamiltonian in here. Right? The Hamiltonian is some kind of a matrix. Okay. So in any case, in the construction of the problem, we essentially settle everything. So however that construction is made, so we can make this approximation in many different ways, actually. But in any particular way that I make this approximation and construct this Hamiltonian, There's also a representation of the symmetric group of that. So there's a symmetric group in here, symmetric group. And from the symmetric group, we can construct representation, right? So I don't know, if there's some kind of a rotation, for example, that leaves this molecule invariant, there's a corresponding transformation of the possible approximate wave functions, which actually does the same transformation, actually, right? So this representation, therefore, is determined by that approximation, right? Let's just keep this in mind, right? I mean, it's not something that we just come up with some kind of new representation each time. No, when we are solving a problem, the representation also comes together with our approximation, right? When we construct the problem, the representation also comes with the construction as well. When we see the examples, we are going to see how these representations are constructed. Okay, so they are definite. So at this stage, when we actually identify the representation, the next step that we should do is to basically decompose it into, decompose it into this block diagonal form by choosing some suitable basis, right? Why do we do this? Because this is going to simplify the Hamiltonian as well. And we are going to see why this is simplified later, right? So as a result, this process is kind of important, right? I mean, basically, given a representation, find a suitable basis which makes this representation to be in this block diagonal form. Okay, there are some certain mathematical problems also in here as well, like how do you find this similarity transformation, or how do you find a new basis, and things like that. But when time comes, we are going to also talk about these as well. So right now, we would like to understand if there is a given representations, is it reducible or not? If it is reducible, how can I decompose it in terms of the irreducible representations, right? This is our first job. There are some certain nice mathematical tools that enables us to do this. Okay, so one of them is something called the Schur's lemmas. So there are actually two lemmas in here. Schur's first lemma is a nice statement. Second lemma is a related statement. So I'm going to write them down one by one. So first one says that if A is an irreducible representation of a group G. So we have an irreducible representation, so it has to be irreducible. And if X is a matrix that commutes with all representation matrices. So let's say it like this. X multiplied with AG is the same thing as AG multiplied with X. So the order does not change, but just keep in mind that this has to be true for all group elements, right? So if this and if A is an irreducible representation and X commutes with all of these representation matrices, then X is a multiple of identity. So this essentially means that there's a number X. Well, so let's say it like this. There is a number C such that X is equal to C times identity, right? So this basically tells you that only identity commutes with all representation matrices of an irreducible representation. If it's not irreducible, if it's reducible, then no, this is not true, right? Let's just keep this in mind. There's a proof in here, but I'm just going to just sketch the proof in here. quickly, so these are also explained in the notes as well. So the idea in here is this. So let me write proof in here, but it's just a very short sketch. So first of all, we solve the eigenvalue problem, right? So let's say that, right? Let V be an eigenvector of X, right? So as a result, X applied on V is equal to lambda V, right? So suppose that we have this. So that's the first step. Second step is that I show that AG applied on V is also an eigenvector with the same eigenvalue. Yeah, whatever. So yeah, basically X applied on AGB, show that that's equal to lambda times AGB. Okay. This is the next step. So number 3 is we just define W lambda. So this is something called an eigensubspace. So this is basically all vectors with all eigenvectors, right? Of V with eigenvalue. Eigenvectors of X with eigenvalue lambda. Right? It's actually a subspace. 0 is also, you can actually think of it as an element of it. So it's really a subspace, right? So the 2 implies that this subspace is an invariant subspace. W lambda is an invariant subspace. Okay. And number 4 is that W lambda is either 0 or W lambda is the full space. Basically, that's the definition of irreducibility. A is irreducible. That representation is irreducible if it doesn't have any invariant subspaces other than the trivial ones. So the trivial invariant subspace is the 0 space and the full space. In any case, since we somehow claim that there's an eigenvector, so that subspace cannot be 0, so therefore it has to be the full space, right? This then implies that in the 4th step, that every vector in the space is actually is an eigenvector, and so therefore the A must be a multiple of eigenvectors, right? It goes like that, but just fill in the details. So the second Schur's lemma is this Schur's second lemma. It talks about 2 different irreducible representations. So let's see it like this. Let A and B be irreps of the group G. Okay. If Y is a matrix such that A of G multiplied with Y is equal to Y multiplied with B of G. So that's for all group elements. So it's not like commutativity, but it's something else. So I can actually think of it like this. Sorry about this. First of all, let me write down the result. So if Y is a matrix such that this is satisfied and that whatever, then, well, there are 2 possibilities in here. Either Y is the 0 matrix. So Y is actually a matrix where all entries are equal to 0, right? That's what I mean by that. 0 matrix is a matrix where all entries are equal to 0. That's probably a rectangular matrix, but in any case, I mean, let's say it like that. So, or Y is invertible. Invertible means that the inverse exists, and A is equivalent to B. if y is invertible, in that case, in this relationship, for example, I can move y to the right-hand side, and then we are going to have this y inverse. Probably I should have actually written this with a different color, but let's just let's just draw it like that. So let's just box this. This is Schur's second lemma, right? So for the second case, if y is invertible, then I can move this y to the other side. As a result, I can do this. So this implies that the A is equivalent to B. They are equivalent representations. Okay. So in a way, if A is not equivalent to B, then the first one is the only possible choice. That's what it says, right? If they are equivalent, then it's possible that Y can be a non-zero matrix, but in that case, it has to be invertible. So we essentially have more or less a single solution in that, more or less, right? I think there's only just a single solution in there. In any case, so let me quickly try to explain this. So let's say that A of G is n by m, and B of G is m by m. So these are square matrices, but Y does not need to be square. So therefore, Y is m by m, right? So we have rectangular matrix in here and a rectangular matrix in here. They have the same size. So Y is rectangular in general. And if n is different than m, of course, it's not possible that this is invertible. I mean, an invertible matrix should be a square matrix. So therefore, if these two dimensions are not the same, the first choice is the only choice, right? In that case, the A and B can never be equivalent to each other, obviously. Okay. Second thing is this, I can actually think of this as like, I mean, I can think of this some kind of an n-dimensional vector space in here. I don't know how to call this, right? And there's an m-dimensional vector space in here. So I can think of this, if A is a n by n square matrix, I can think of A of G as a transformation in here and B of G as a transformation in this other vector space, right? And in that case, let's see, Y is a map from this vector space to that vector space. Okay, so this then tells you that this relationship, what does it tell you? Well, I don't know what it tells you. It's not something that's easy to interpret. So if you have a vector in here, you first symmetry transform it and then map with Y. This is the same thing as, well, you first map with Y and then symmetry transform it in here. Right? Something like that. What does it mean? I don't know. I mean, but I mean, at least you can think of Y as a map between two different vector spaces. And if the dimensions are different, that explains why Y is a rectangular matrix. Okay. So the proof goes like that. First of all, you can show that the kernel of Y, which is a subspace in here where the Y is takes on, maps the vectors to the zero vector, basically. So that's the kernel of Y. So show that this is an invariant subspace of B. Okay, which means since B is irreducible, this means that either the kernel Y is the zero subspace or the full space. Okay, in each case, you mean it means something else. I'm not going to show this to you, but you can easily show that. Image of Y, so image of Y is a subspace in here. So basically all vectors in that subspace map to vectors in here. So it's also a subspace. So show that this is also an invariant subspace of A. Okay. In that case too, image of Y is also either a zero subspace or a full subspace because A is irreducible. Right? And number three, let's just say it like this. If Y is the zero matrix, sorry, it's not if. Y is the zero matrix is the same thing as saying that the kernel of Y is the full vector space in the domain. That's the same thing as the image of Y is the zero subspace, right? So that basically corresponds to that situation. So in that case, if Y is not the zero matrix, in that case, this is not true. So therefore, this then implies that the kernel of Y is the zero subspace, which means that, well, this is not invertible yet, but it's one-to-one. And the image of Y is the full space, so therefore it covers the full space, which, I mean, both of them should be true, so therefore this implies that Y is invertible. Okay, so when it's invertible, then we can do the rest. Okay. Okay, so these are Schur's lemmas. So these are going to be useful, actually. Why they are useful? Well, I mean, let me say it like that. I'm going to come back to this later. Symmetry statements for a physical problem can be expressed as the commutativity of the representation matrices of the group elements with the Hamiltonian. So we are going to think of these as matrix problems. So therefore, it's just the commutativity of the Hamiltonian with the matrix, right? But this is not irreducible usually. It's going to be reducible. But if I decompose this into this in this block diagonal form in terms of the irreducible ones, then this relationship can become useful through the use of these Schur's lemmas, actually. And so as a result, I can say something about some certain blocks of this Hamiltonian, right? I can say that some certain parts of that Hamiltonian are zero matrices, or some of them are multiples of identity and things like that, by using Schur's lemmas, all right? So by using this commutativity relationship, I'm going to say that this matrix is going to have some simpler form, right? So the Schur's lemmas actually enable me to do this in a systematic way. All right. So the next thing that I'm going to do is this. Okay. Let U mu and U nu be any two irreps of. Okay, so all of our groups are finite, right? So sometimes I'm going to state this, sometimes I may forget. So from now on, I'm going to assume that all groups are finite groups, because some parts of the proofs are actually going to use the fact that the group is finite, right? But so I may actually forget about this. So we will never do a representation theory of infinite groups, unfortunately. Because in applications, especially for molecular physics, the symmetric groups are usually finite groups, and there are only a few of them, actually. We don't have much. I mean, there are lots of groups, like around 30 groups or something like that. And for each one of them, I mean, we know how to find the representations and things like that. Okay, let's just take any two representations. So mu can be the same as mu. I don't know, that's possible. It can be different. The dimensions can be different. So we know that this has dimension d mu and this has dimension d mu. So what I'm going to do is this, right? So let X be any matrix of size d mu by d mu. It is rectangular or square, I don't know. So I'm just going to define a new matrix. So there's, first of all, there's a summation over all group elements. I'm going to multiply u mu, Hermitian conjugate of u mu. Basically, this is the inverse of that matrix because u mu is unitary. In any case, let's just write it as Hermitian conjugate. I multiply this with X matrix from left, and then from right, I'm going to multiply it with u and u. Okay. So in any case, the nice thing about this matrix is that this satisfies Schur's lemmas conditions. So as a result, we can show this. I'm not going to show it in here. Y multiplied with u nu of h is equal to u mu of h times y for all h in the group. Okay, which implies that, well, basically, this implies that if mu is different than mu, so these are different representations, then y is equal to 0. Because I mean, in the Schur's second lemma, let's just come back to this. Schur's second lemma, there are like two conclusions. Either y is equal to 0 or it is invertible. All right? And if it is invertible, then these two representations have to be equivalent. If they are not equivalent, then 0 is the only choice in here. So let me just say, instead of 0 in here, so let's say that this is 0 matrix. Okay? And if mu is equal to nu, then, well, in that case, Schur's first lemma applies, and y is just a multiple of identity. In that case, that's what we do, right? We just write down C times identity in here, and then write down this relationship, u mu dagger g x u mu. Okay. I mean, we would like to then compute the coefficient in here. So that's the problem in here. To do this, we just do a very simple trace calculation. We first of all write down this relationship, of course, obviously for the same representations in here. Right? Otherwise, I know that the left-hand side is 0. So I just take the trace of both sides. So that's trace of u mu dagger g x u mu. Later, I'm going to show this property of the trace. So it's basically cyclic property. I can move this matrix and to the end of the expression here. So therefore, I can write this thing down as the x times u mu. So that's x times u mu of g multiplied with the u mu dagger g. So that's the same thing as the trace of this one, but this is equal to identity. So therefore, within the summation, I have the trace of x. So for all g's, I have like this matrix has the same trace as this one. And so therefore, on the right-hand side, I have g in here and the trace of x. On the left-hand side, I have c and the trace of identity, which is equal to the dimension. So that's the order of the group, right? The number of elements within the group. So from here, we can find what c is. Okay. In short, I can basically summarize this relationship like that, right? I'm going to do it like this. Sum over the group elements of u mu dagger g x u mu of g. There's a sum over the group elements. That's equal to the order of the group divided by the dimension. Delta mu nu, so if mu is different than mu, that's right-hand side is definitely 0. These are inequivalent. If mu is equal to nu, in that case, I'm going to write this expression in here. I already written this, so therefore this is trace of x. Okay. What we usually do is like we just move this g to the left-hand side. So as a result, on the left-hand side, I have something like that. It's kind of easier to remember like that, because in that case, I can interpret the summation and division by the number of elements of the group as some kind of an average of this expression over the group, right? I mean, this is a function of the group elements. With this, I'm taking an arithmetic average of that function, right? That you can think of it like that. Okay, now this is arbitrary. Now, what we do after that step is that, well, just take these matrices, X matrix as a matrix where all entries are equal to 0 except one entry in here, somewhere in here. I don't know, which entry, for example, I don't know, the ijth entry, for example. Sorry, that's the ijth entry. But that's the ith row and jth column, for example. Sorry, there's an identity in here. Sorry. Yeah, whatever. In short, I'm just going to write down the final relationship in here. So that's 1 over g times sum over the group elements. Here, I'm just going to write down the matrix elements. So that's the u mu of g, pi. P and I are just integers. We just have the complex conjugate in here. And then u mu of g, qj. That's equal to 1 over d mu, delta mu nu, delta pq, delta ij. Right? That relationship is called the orthogonality of the matrix elements. What does that mean? First of all, I'm going to think of it like that. Okay, I mean, think of it as some kind of an explanation. So group has many elements. So let's just say that, well, it has an element G1, G2, whatever. So the last element is, let's just say it like that, right? So each representation is actually a matrix, right? U mu of G's, for example, each one is a matrix. So I don't know, let's say that this is a 3 by 3 matrix, right? So if this is identity, then that's the identity matrix, whatever. But let's just show it like that, right? I have also explained this in the class like that. So as a result, we have this many matrices. Probably each one of them will be different from each other. Okay. U nu is going to be another representation. Let's say it might be the same representation, might be different, but let's say that it's a different one. Okay, so let's say that this is two-dimensional now. So we have a 2 by 2 representation. So what we do is this. We choose a p value, let's say the second row, and an I value, right? So here, I'm basically taking the mute representation and the pi matrix element of that representation for different group elements, right? Essentially, I'm looking at these elements in here. So the elements in the same place, right? Elements of different matrices in the same place. I basically get a set of numbers in here and the total numbers, complex numbers. All of these complex numbers, there are G many complex numbers. So the number of complex numbers in here is equal to the order of the group. And then I look at another matrix element in here. So let's say that Q is the second row and the J is the first row, right? First column, sorry. As a result, we are looking at this particular matrix element. Okay. So we have like this yellow matrix elements and red matrix elements, right? There are same number of numbers in there. So what I do is I basically take the complex conjugate of the, let me use a yellow coloring here, complex conjugate of the yellow matrix elements and multiply it with the red matrix elements in here. Basically, I'm multiplying these two numbers, right? And these two numbers and adding them up. This is like an inner product, but I'm taking the inner products of some matrix elements, actually. Okay, so it's some kind of an inner product, actually. This tells you that these inner products are different if either the representations are different or the matrix elements are chosen from different places, right? So there's some kind of an orthogonality relationship of the some carefully chosen set of numbers, right? So think of it like that, right? In real applications, we don't actually use this relationship, but in deducing some other relationships, this is actually an important stepping stone, but you have to understand what this means. Okay, so in any case, there's one important thing in here. Right, this is an orthogonality relation. Orthogonality means perpendicularity, right? Relation in an G-dimensional vector space. So this is just a mathematical vector space, right? It has no physical significance at all. Nothing at all, right? We don't have any physical applications in here. But I can think of the set of numbers in here as the components of some vector in some G-dimensional vector space, right? And so therefore, these different vectors are perpendicular to each other. There's also a normalization relationship in here when the right-hand side is non-zero. You get a normalization too, but that's unimportant at that point. Sorry. In any case, so since in this G-dimensional space, there's actually that many possible vectors. So for example, for that representation, I can find 9 vectors because we have 9 matrix elements in here. For that representation, I can find 4 vectors. Right? In each case, I can find the number of vectors from each representation is equal to the d mu squared, because every square matrix with that dimension has d mu squared matrix elements. Okay? So that means in that vector space, I can find at least this many vectors, and they are all perpendicular to each other, which means that the dimension of the vector space should actually be bigger than these. Okay. In any case, later we are going to show that it's actually an equality, but right now we cannot show this. But this actually tells you one important thing. Well, there can be only a finite number of irreducible representations, because if I have an infinite series in here, the left-hand side can never be finite, right? So there can be only a finite number of terms in here. There's only a finite number of irreducible representations, and the sum of their dimension squares is bounded by the order of the group. Okay, but as I said, let's say that this is the correct form. It is really there is really an equality in here, but that's actually one of the important relationships that we are going to use when we analyze the group, right? Okay, so let's finish it in here. So next week I'm going to summarize also these the characters and how to use characters to say something about the irreducible or reducible representations. Okay, so let's finish this.